Good evening, friends. I'm CV Sharma. I'm back with another video here, and then that's motion with non-uniform acceleration, and then this is a theory part and the use of definite integrals. This is the idea which I'm showing you, and this is the notes for you. In all the videos, I'm providing the notes for you so that you'll understand the chapter in a very detailed way. And then I'm planning to make more than like 200 videos per chapter, so that the small videos, 200 small videos, so that you will understand the chapter without any bore. It will not be like continuous lectures. So it will be like short videos in which I will I'll explain different problems in each video so that you will grab the concept. So here we go. This is the displacement function delta x is equal to integral t1 to t initial to t final v of t dt. So when you integrate the velocity, when you integrate the velocity function under the limits t1 to t2, then you get what you get is a displacement function. Okay, displacement function is what you get, and when you put the limits like t initial to t final, what you get is displacement for the time interval t initial to t final. This is what you get. Okay, this is a definite integral from t initial to t final. That is what I hope you all know how to do the definite integrals. So just depicting the idea. Similarly, the change in velocity v delta v happens to be integral a dt. So these are the simple concepts. So while solving the problems, you will understand how do we exactly do this, how do we exactly use this. So this is nothing but this integral, definite integral is nothing but the area under the particular curves. This is the area under the VT graph, that is displacement. There is the area under the AT graph, that is acceleration time graph, that is change in velocity, right? And these equations are useful for solving the problems under the non-uniform acceleration. When you have the acceleration as a function of time, so in some questions, the acceleration will be given. Acceleration will be given as a function of time. Function of time. In that particular scenario, these equations are very useful. Then you have to use the integral methods to solve the problem. So that is what is I am explaining here. So there's a notes directly. You can pause the video and then you can make a note. The acceleration depending upon the velocity v or time t. By definition of acceleration, we have a is equal to dv by dt, and then in terms of t, you can use integral v naught to v. That's a change in velocity on the left side, and then dt you transport to the other side. Integral a dt, the time is from 0 to t. If a is in terms of velocity, then you can have integral v naught to v dv by a v. So integral 0 to t. Sometimes they give you acceleration in terms of velocity. So that is also possible. Next one, if you were given the displacement as a function of, so velocity function is given, and then you are asked to find the displacement, you can use this equations. Okay, so you know that velocity is dx by dt, and then dt you transport to the other side. So you have dx is equal to v dt, and then you have to integrate on either side. So that is a basic idea here, and then that is depicted in this particular integral. Okay, so the time limits can be like t1 to t2. Okay, they have taken like a 0 to t time. It's up to you. So okay, that displacement can be like 0 to x or x naught to x. So it is between 3 seconds to 5 seconds, between 3 meter to 5 meter, between 3 seconds to 5 seconds, between 3 meter to 5 meter. Like this, they can twist the question and they can give you. So these are easy ones only. It's not that difficult. So how do you do the acceleration in terms of velocity? This is what I explained to you in the last video. It's pretty simple. Acceleration is that, but this concept is very important concept. Very important concept. All of you have to know this. So acceleration is dv by dt, acceleration dv by dx into dx by dt. Like this, using a chain rule, you can do that. And now the dx by dt is nothing but the velocity. So you can put up that's velocity v into dv by dx. This is very, very important. So this I depicted in the earlier video. You can see that. And then this is another important expression for the acceleration. Integral v dv v naught to v is nothing but integral x naught to x a f x dx. If a is in terms of velocity, so then integral v dv divided by a of v, that is equal to integral x naught to x dx. On integrating, we get the relation in x and v. So after that, I hope you understand. This how you get the on integrating, we get the relation between x and v. Using integral x naught to x dx by v of x, if the velocity is depicted in terms of displacement, you can use this expression to relate x and v. Okay, I hope you understood. This is a theory part, and then in the next video, I'll move on with the problem. Next, the problems will be I'll be explaining. I hope you understand this, and then please make a note of the notes, and then you can pause the video and make a note. I'm showing the entire notes here, so you can have a look and then note the things. Okay. And thank you all. Thanks for watching the video. And, hope you like. Please like, do like, and subscribe and share. Thank you all.